Well, this is great and all. So we know that left leg strength has the most variation explained by other covariates. What should we do? We could just go ahead and use the model with all of our collinear covariates and only use that model for predicted values of y hat. Again, that is not going to have an effect on our fitted values. Where multi-co-linearity is going to be an issue is with the estimated coefficients, right? We're not going to be able to attribute where the variation is explained, but the model is still doing a good job of explaining the variation and the outcome. Again, this model isn't going to be very useful though. What would be more helpful would be to drop variables that are highly correlated with the other covariates. Or what we could do is we could create maybe like a composite variable where we could just add things together, or maybe we know that there's kind of a composite effect. So if there's strongly correlated, maybe x3 is doing most of the work. So that would be 50% to this additive variable. And then maybe x1 and x2 would make up the remaining portion of that variable, and that would be a new covariate that we would use to help explain variation in our outcome. Or what we won't have time to talk about in this class, but if you're interested, you could certainly look it up or take further classes, would be principal component analysis. And essentially what this does is it tries to reduce these multiple dimensions to one simplified common dimension that helps explain the way that these variables covary together. To summarize our thoughts on multi-co-linearity, I think it's really important to note that if we do have collinear covariates, we're not necessarily violating any assumption, but it is important to look at because we are biasing the estimated partial effect of each covariate, right? We're unable to identify and attribute what variable is actually doing the work. We're unable to attribute what variable is truly driving the underlying relationship between our predictors and our outcome. And unfortunately, this problem can occur if we have just a pair of highly correlated variables or if there's a large group of only moderately correlated variables. So this is really important for us to take the time and look to see whether or not collinearity is a problem, because it's going to introduce a lot of issues into our analysis if we're not careful. Now, a thing to remember is that if you include interaction terms in your regression model, you're kind of automatically introducing some collinearity, right? You're artificially saying that the effect of one of your covariates differs based on the value of your other covariates. But the important thing to remember is that if that is the true data generating process, their inclusion, the inclusion of those interactions, is necessary, and it's going to be really important for you if you are to actually get estimates that make sense and are reliable. Now, I know it's been a couple of videos, so I want to give you pleasant reminders of how we can also go about solving other problems other than multi-collinearity. So, if we have outliers specifically with regard to our independent variables, we can check for high leverage by looking at our hat values and seeing if they potentially are influential on our fitted values. We can also look at our studentized residuals to see if they are quite large with regard to outliers in our outcome. Now, the combination of those two is influence, and that will be impacted, or we can check for that with regard to our Cook's distances or our DF betas, right? The difference in our estimated coefficients. These can suggest points that are going to have a big effect on your regression coefficients and the fitted values. We can also look at observations that have large Cook's distances, meaning that they together have large leverage and studentized residuals. They're outliers in both our X and Y space. And that, again, is going to have potentially a large impact on our regression coefficients. We also discussed how to find and diagnose jointly influential points using added variable plots. Finally, don't forget that we need to check whether or not our assumptions actually hold, and we talked about this in a previous module with regard to regression diagnostics, but I want to bring it up again just as a pleasant reminder. To check for non-normality, we look at our QQ plots of the residuals to see if they follow a linear line and if they deviate from that kind of 45-degree angle from the origin to the top right corner. We also need to look for non-constant variance, and we can do that by checking the residuals versus the fitted values. So they should be pretty randomly dispersed along a horizontal line. They shouldn't have any relationship whatsoever, or we can look at added variable plots. We also need to check for nonlinear relationships, and again, we can use added variable plots or just using bivariate scatter plots. To conclude, what we talked about in the last couple of videos in this module is multi-co-linearity, and we can look for covariates that may covary with each other by checking the variance inflation factors. And again, I think just looking at scatter plots in general can help figure out which covariates are likely to induce multi-co-linearity.